So now that we've reached this point, one thing I may have mentioned this before, but one thing we can notice is that this equation we've now derived with these macroscopic quantities is looking very similar to the ideal gas law. Right, we have PV on one side, we have a bunch of other stuff on the other side, and let's start to make some comparisons here, right? So we want to compare this to PV equals nRT. Well, one of the first things we need to do is these values here, big N and little m, these are both for individual particles, right? So N is equal to the number of particles. This is not in moles, this is an absolute number here. Whereas little m is not the molar mass, but it's the mass of a single particle, whether that's a single atom or a single molecule. But everything we have in the ideal gas law is in terms of moles. So we want to be able to change this to molar quantities. All right, so if we take big N and divide by Avogadro's number, that'll give us the number of moles, which we call little n. And if we take little m and multiply it by Avogadro's number, that'll give us what we call capital M here, right? So little m here again is the number of moles, and capital M here is the molar mass, right? The mass now of a mole of particles. So we took the mass of an individual particle and multiplied by a mole, Avogadro's number. And we can see if we multiply big N times little m, that's going to be the same as little n times big M, because the Avogadro's numbers here, we're dividing this one and multiplying this one, they're going to cancel out. So we can make a direct substitution here and say, okay, from our equation up here, we have PV equals 1/3 little n times big M times absolute value of the square of the average, not absolute value, the average of the square of the speed of the particles. Okay, so now we have n's here, right? So we can say, we know this is equal to PV, this is equal to PV. We can set these equal to each other. nRT is equal to 1/3 n big M average of mu squared. And now we can see the n's are going to cancel out, and we can solve for the average, the root mean square, RMS. So the average of the square of the speed. All right, so we're going to multiply by 3. So we'll get 3RT divided by big M is equal to the average value of mu squared. Okay, and so one thing we often do with this is to get something that is not quite, it's not exactly the average speed, but it's the root mean square. Root mean square, RMS speed, is if we take the square root of this value. So we take the root of the mean of the square. That's where this root mean square comes from. This is not exactly the same, it's just the average speed, but it's pretty close. That will be equal to the square root of this. Right, so 3RT divided by big M. And so we can see the speed of the particles depends on a couple of things that we have here. So we have T to the 1/2. This is something that will change, right? So this is temperature. 3 and R are constants. And we have 1 over M to the 1/2. So I want you to pause real quick and think, what does this mean? Looking at this equation, what does this tell you about how temperature and molar mass affect the average speed of particles? Okay, so we can see that if we increase temperature, the average speed will increase. And if we increase mass, the speed will decrease. Right? These are inversely proportional. So if we have higher temperatures, the particles are moving faster. If we have lower temperatures, they're moving slower. And if we have larger masses, they're moving slower. Smaller masses, they're moving faster. Right? So this is some information we can get about what's happening with the particles. Now this just tells us an average. It doesn't tell you what's happening with a single particle. As you may have remembered looking at the PhET simulations, some particles will be moving fast, some will be moving slow, but this is just talking about the average. Okay, and we'll go ahead and pause here because the next thing we'll be talking about is not averages, but the distribution of speeds.